Good morning, my YouTube viewers. It's Crystal here, and I wanted to give you a code review. This code review is going to be on the Diamonds data set, and it's a Kaggle competition question. And so I think I've worked on the Diamonds data set in the past, but this is the first time that I've worked on this particular Diamonds data set. And what I want to do is I want to go through the code that I used to get the answer. So I had a score of 1.4.0899, which was about the middle of the leaderboard. So I just want to show you what I did to get that score. And what I did was, it's a Kaggle community competition. I used Kaggle's Jupyter notebook, which is free, and it's stored in my account. And what I'll do is I will leave a link to the Jupyter notebook in the description box down below of this video, so you can look at the Jupyter notebook if you want to. So the problem statement for this one is predict on the price of diamonds. So that's what we're doing. We're predicting on the price of diamonds. And then we created our Jupyter notebook, and we're going to import the libraries. And the libraries we're going to be using are NumPy to create NumPy arrays and perform numerical computations. We're going to import pandas to create the data frames and perform data processing. We're going to import OS, which goes into the operating system. We're going to import SciPy, which performs scientific calculations. We're going to import sklearn, which provides machine learning functionality. And we're going to import TensorFlow, which creates the neural network. And we're going to import matplotlib.pyplot_splt, which visualizes the data. And we're going to import clearn as SNS, which visualizes the data statistically. So after we've imported the libraries that we're going to need, we're going to use OS to go into the operating system and get the files. And in this instance, we only got a train CSV file and a test CSV file. So we're going to have to create our submission file because they didn't give us a submission file. And then we're going to use pandas to read the CSV files into the program and convert them to data frames. So the train CSV file is going to be called train converted to train, and the test CSV file is going to be converted to test. So you can see the train CSV file here where you've got ID, caret, cut, color, clarity, depth, table. Then you've got XYZ and price. And they don't tell you what XYZ are. Those are just some extra columns that they put in there. We check for null values, and we don't have any null values. So that's good. We don't have anything to impute. We checked info, so you can see we've got the ID as an integer, and everything else is either a float or an object. And the thing about XYZ, they don't tell you anything about XYZ. They don't tell you what XYZ is for. They just say XYZ. So test is the same as train, except for the fact that it doesn't have the price. We check for any null values in test, and we don't have any null values in test. And then what we have to do is we have to create our submission file. So train equals train.drop ID, axis equals 1. Submission equals pd.dataframe. Submission ID equals test pop ID. And this is your submission. where you get one column that says ID, but we're going to build the submission file at the end of the program, so don't worry about that. Now what we're going to use is we're going to use the Kolmogorov-Smirnov test. I believe that's what they call it. And we're going to check to see if the columns in train and the columns in test are from the same distribution. And if they're not from the same distribution, then we will remove those columns. But fortunately, all of the columns were from the same distribution, so we didn't have to do that. And it's called I'll show you what it's called. It's called Kolmogorov-Smirnov test 2 columns. That's what it is. And then, so I started doing that. I started testing to see if the test data set is from the same distribution as the trained data set, because if the test data set is not from the same distribution as the trained data set, then there's going to be problems when you go to predict, which I've had that problem in the past. So now what I want to do is see if there are any columns that are not from the same distribution. Now we're going to analyze train. So we're going to take the target out. So target equals train.popTarget, and we create a histogram of that using Seaborn. So sns.displayTarget, KDE equals true. So this is your distribution, and so of the price. Now what I wanted to do is I wanted to do a scatter plot on a carrot versus the target, and you can see that typically the higher the carrots, the higher the price. So the more carrots you have, the higher the price is going to be. And now what I want to do is I want to check for the unique columns in the object column. So for call and train, if train call.dtype equals object, print call, comma, train call.unique. So I want to see what the unique values in the object columns are. And so for the cut, it's going to be good, very good, premium, ideal, fair. For the color, it's going to be DHEGFIJ, and then they give you some clarity symbols as well. So I created a box plot for the cut. So SNS.boxplot, data equals train, X equals cut, Y equals target. So you can see typically the premium cut is higher price than the other cuts, and that's what you would expect. Now we create a box plot on the color. So you can see typically the color J is a higher price than the other colors. Now we do a box plot on the clarity, and so you can see typically VS2 has higher price than the other clarity labels, clarity classifications. Now what we want to do is we want to encode the columns that are object. So from sklearn.preprocessing, import ordinal encoder, ENC equals ordinal encoder for call and train. If train call.dtype equals object, train call equals inc.fit transform, train call.values.reshape -1, 1. And then test call equals inc transform, test call values.reshape -1. And so you'll notice that the first one for the train I did fit transform, And for the test, I just did transform. And then previously, I'd used something else. I had put both of them to be fit transform, and I didn't get as good a score. So the train is going to be fit transform, and the test is going to be transform, and that gave me a better score. So here we can see train, now that we have encoded the object columns. So now the object columns are given numbers. So now what we're going to do is we're going to create a heat map. Core equals train.core, SNS dot heat map core. So this is your heat map. And you can see when you do the heat map, you can see the X, Y, and Z have a high correlation. So you can see that from the heat map. And then what we do is we print off core, and you can see again from the heat map, X, Y, and Z have a high correlation. So now what we want to do is we want to remove the columns that have a high correlation. So core matrix equals train.core.abs. So what that's going to be is the absolute value. And the reason why that is because the correlation can be anywhere from -1 to +1. So 0 is no correlation, but it can be anywhere from -1 to +1. So you do ABS to make it absolute value. And then you select the upper triangle of the correlation matrix. So upper equals core matrix dot where NP true NP dot ones core matrix dot shape K equals 1 dot as type bool. And then you find the features with the correlation greater than 0.95. And then to draw equals column for column in upper dot columns if any upper column is greater than 0.95. And then I put print dot to draw so you can see which columns they're intending to draw. And now we've dropped the features in the train dataset and the test dataset. So now you can see train, we don't have X, Y, and Z anymore, and you'll have the same thing for test. Now what we do is we define our X and our Y variables. So your Y variable is your target, and that is a dependent target. It's dependent upon the X variables. And your X variable is train, and all of the columns in the train file are independent. And when the columns in train file change, then that's going to change your target. And then X test is your test file. So now what we do is we use sklearn train test split to split the X and Y variables up into training and validation sets. So the test size is going to be 10%. Random state is 42, and then it takes the input of X and Y as your arguments. So X train, X val, Y train, Y val equals train test split. X, Y test size equals 0.1. Random state equals 42. And then what we do is we check the shape. So you can see on the X's, you've got 6 columns, and on the Y's, you only have 1 column, which is a series. Now we're going to get into the point where we are creating our neural network. So we're going to have to import TensorFlow. So we import TensorFlow and its related libraries and modules. You see that we're using version 2.12 on TensorFlow now. Previously, we had been using 2.11, and TensorFlow goes through a lot of changes. And because TensorFlow goes through a lot of changes, you have to stay abreast of those changes. And then generally, what happens is if you upgrade your version of TensorFlow, then it's likely you're going to have to go through and make changes to your code because certain functions will become deprecated and you won't be able to use them any longer. So we're going to create the first line of our neural network with the standardization. So normalizer equals normalization, axis equals -1, and I think that means that you are going to normalize all of the columns. Normalizer.adapt np array xtrain, and then we print normalizer.mean.numpy. So what you're printing is the mean of each column. And then so what we do here is we're going to do a little experiment. So you can see the first row of the xtrain that hasn't been normalized. And then you can see the first row of xtrain that has been normalized. And now we create our sequential artificial neural network. Model equals sequential, name equals diamond prices, model.add normalizer, model.add dense, and then I selected 10 neurons. And the reason why is because I did some research about how to select the most appropriate neurons, and basically what they say is it's trial and error, and they're saying one thing that I read was that the neurons are supposed to be less than the total inputs. But whenever I look at pictures of an artificial neural network, the number of hidden neurons is always more than the number of input neurons. So if our input was 6, then I'm going to make the hidden neurons 10. So we had 10 hidden neurons, and I could have said 6, but I didn't. Activation is ReLU, and name is hidden 1. And so basically ReLU is similar to sigmoid, except all of the negative values are converted to 0. And that's the difference between ReLU and sigmoid. And then ReLU also has some different problems with it as well, because I made a blog post on how to select the best activation optimizer loss functions. And there are other activation functions that you can use besides ReLU. And I suppose that if I was really interested, I could try out some of these other activation functions and see if it improved my score. That's something I could try. And then the next layer is model.add dense is 10 neurons, activation equals ReLU, name equals hidden 2. The next layer is model.add dense, activation equals linear, name equals output. And then you can see the summary of the model. So this gives you a summary. So one thing that I could try is I could try different activations on the hidden layers and see if that improves my score. That's one thing I couldn't, because there are some problems with ReLU. Now what we're going to do is we're going to compile the model. Loss equals mean squared error. Optimizer equals Atom, and metrics equals MSE, which is mean squared error. Atoms is a very good optimizer, but you can also use SGD, and you can also use RMS prop. But typically, people use Atom because it's a very good optimizer. And then we're going to set it up for early stopping, and we're going to set it up for a model checkpoint, so it will save the best model. And then after do that, we're going to train the model. So history equals model.fit, xtrain, ytrain, epochs equals 100, validation data equals xval, yval, batch size equals 32, callbacks equals early stopping, MC. And then we're going to evaluate the model. So val loss, val ac equals model.evaluate, xval, yval. So we set it up for early stopping, so it's going to stop before it reaches 100 epochs. And then you can see the MSE is 0.312. So I created a graph so you can see the MSE, and you can see that the MSE for the train and the validation sets are very similar. We predict on our xval, which is your validation set, and then when we predict it on the validation set, what we do is we get our RMSE, and your RMSE is 0.17. And then I created a graph of the predicted values against the actual values, and I think it looks okay. You got a few outliers, but other than that, it looks okay. And then we create a data frame, and what this data frame will do is it will give you your actual values and your predicted values, and you can compare them. And now we're going to predict on the test set, and we're going to use the same algorithm that we used to predict on the validation set. And what I did was I created a histogram of the test set to see how the test set predictions compared to the target and the train set. And then what I do is I prepare the submission. So submission price equals predictions, submission.toCSV equals submission.CSV and x equals false, submission equals pd.readCSV, submission CSV submission, and then here is your submission data frame, which we have converted to a CSV file. And so whenever I saved my work and submitted it to Kaggle, I got a 1.4, which was about the middle of the leaderboard. But I think when I finish this code review, I'm going to see if I can experiment with a different activation function and see if that improves my score, because you never know, it just might. So thank you so much for watching this video. Thank you to my subscribers for supporting my channel. If you like my video, please like, subscribe, and share. If you want to be notified whenever I make a new video, then please tap onto the bell button next to the subscribe button. And I don't know if my viewers have noticed this, but I'm trying to speak more slowly when I make a video, because I'm hoping that if I speak more slowly, then I'm a lot more clear in what I'm saying, and I can make better quality videos. So if you have any thoughts on that, please let me know what you think. Do you think the videos are better when I speak more slowly and try to be more clear and more concise? Because I really would like to know my viewers' opinion on this. So thank you again for watching this video. I look forward to making more videos and code reviews for you in the future.